Okay, let's get started on this practice test for heat. It's not even chapter 7 and 8, it's actually 5, 6, and 7, but this is such an old sheet. Let's go through the questions. The first one says, how much work is done to push a box 3.5 meters with a constant force of 30 point. So question 1, these are knowledge questions, so they're nice and straightforward. Force 30.4, and I pushed it 3.5 meters. No crazy angles or anything, just straight up. So 30.4, 5 is 106 joules of energy. Okay, number 2. How much kinetic energy does a 1,500 kilogram truck contain if it's traveling at 150 kilometers an hour? That's not standard scientific units, so divide by 3.6, it's 41.66, repeat, meters per second. Kinetic energy equals mv squared over 2. Got the mass of the truck is 1,500 kilograms. The speed is 41.66, repeat forever, divided by 2. That number is already on the screen, so I'm just going to square it, times 1,500, and then divide by 2. Okay, probably better to go on scientific notation for that one. Okay, number 3, efficiency. You got a 60 watt light bulb, it's only producing 4 watts of light. So efficiency says, how good is this device? The other 56 watts is going just straight into heat. This must be one of those old light bulbs, incandescent ones, but percent efficiency is your output, which is what you get in the end, divided by your input, which is what you pay for, times 100%. This one's basically the electricity that goes in. Output is the light that we want, so that'll be 4 divided by 60 times 100. 4 divided by 60 times 100. Is 6.6666, so 6.7% efficient. That's A. B says, where does the waste energy go? Well, it'll be heat, and that's just going to go into the room, wherever that light bulb is. Okay, unless it's a heater. Electric heaters are always 100% efficient because that's usually our waste heat. Okay, what do we got here? I think we can squeeze this in here. 4. 85 kilogram student is on the edge of a 30-meter cliff. How much potential energy? Okay, EG equals mgh. Mass is 85. Gravity on Earth is 9.8. And they're 30 meters in the air. So 85 times 9.8 times 30. We got 24,990 joules of energy. That's potential energy just waiting to turn into something else. Student falls over the edge. How much kinetic energy will the student have just before striking the ground? So just before he hit the ground, so here he is up here. You let go of him, his initial velocity is 0. He has no kinetic energy. It's all potential. Just when he gets to the ground, H equals 0, so EG is now 0. All of the potential energy is turned into kinetic energy. So there's no math in this question. It's just EK will be the same number because there was 100% transfer from EG to EK. It's one of those nice questions where velocity is 0 at the start, and then the other term, H is 0 at the end. Just energy is perfectly transferred across. Okay, let's take a look at number 5. Number 5 says, state how you can transfer energy. So there's convection, conduction, and radiation. Okay, convection is the movement of fluid, which could be gas or liquid. Conduction is contact. You're physically touching something, the molecules on the one are banging into the molecules of the other one. And this one travels through the air. It's kind of like light. Okay, this one you can reflect. Okay, this one you just have to avoid contact, and this one you have to get rid of any fluids that might transfer the heat. So if you look at like a really expensive thermos, inside the thermos there's always this glass container. well, they'll be inside some other box like this, but there'll be a lid on the top. Let's put a coating around the outside. I guess the little valves on there. And then this is always, it's always a silver color. Okay, that reflects the radiation. And these 2 layers of glass, these are expensive thermics. You're looking at shiny silver and it's glass. If I look inside, it's shiny and there's 2 layers of glass, and in between the glass, they suck out all the air. It's a vacuum. All the air has been removed. There's no molecules. Okay, so if there's no molecules, there's no contact from the inside to the outside. There's no motion of fluid. So this kills both. It stops conduction and also stops convection. Like if you left the air inside here and say you had some really hot soup in here, then the air molecules here would touch the hot soup. They would rise up here, cool off, and then come down this side and give all the heat off to there. Go round and round, just like a conveyor belt, just taking the heat out. Okay, but that's the knowledge part of that test. Let's take a look at the thinking parts. Okay, question 1. There's that 1,500 kilogram truck again. And it goes from rest to 110 kilometers an hour. Let's get that into some normal. Divided by 3.6 is 30.55 meters per second. That's how fast the truck is going at the end. So basically we're asking for the power. That's saying how much work did this truck do every second speeding up. So work could be any form of energy. If you're lifting something, it's gravity energy. If you're going fast, it's going to be kinetic energy. So we're going to find EK. I got the mass of the truck is 1,500. The velocity, 30.5 repeat squared divided by 2. The velocity is on the screen, so just square that number times 1,500 divided by 2. And I got 700,000. 231 joules of energy went into that truck. And it did it in 6.2 seconds. So power equals work divided by time. In this case, it's EK. It could be EG, it could be heat, it could be nuclear power. Any form of energy is in there. So we can stick the numbers in. 700,000, 231 joules, 6.2 seconds. So that number's already on the screen. It comes out to 112,940 watts. Again, they also want horsepower. Horsepower is 746 watts. Okay, so if I divide that by 746, I get 151 horsepower. Okay, that's an old term. We used to use horses to plow the fields, but we've since pretty much use watts now. Race cars still talk about horsepower. It just sounds cool. Okay, teacher of unknown mass rides his bike over a jump. He leaves the edge of the jump, which is 1.2 meters. And the velocity is 15 meters per second. And it goes up, and it comes back down again. He's still going 5 meters per second at the highest point. Okay. Line here. He's still going 5 meters per second at the highest point. And we want to know the height. This is one of these E-total questions. So I need to find somewhere in this question where I know both velocity and the height. So I can get both terms there. Here, they give you the velocity, but I have to find the height. But the total stays the same. It's constant for the whole question. So at this point here, we can find E-total. Okay, so I got to add up the two things. Oh, we're missing the mass. Well, you can just assume the guy weighs 60 kilograms. You can make any assumption you want because the mass is going to cancel out. Or if you're not too scared with the math, you could leave that M there. And I fill everything I know. The velocity is 15 over 2. So 9.8 times 1.2. That's 11.76 times M, whatever M is. 15 squared divided by 2 is 112 M, whatever M is. Add those two numbers together. 124.26 M. That's my total energy. And that's in joules, and this would be a number. If it was a 100 kilogram person, that's nice and easy. Just move the decimal spot over 2 spots. Okay, let's go to this part here. This question, we want to find the height. So at that point, E total will equal mgh plus mv squared over 2. E total is constant, so I have that number. So 124.26 equals unknown mass times 9.8 times an unknown height plus unknown mass 5 meters per second squared over 2. Oops. So I'm on that guy too. Everybody knows it's everywhere though. M. Everyone's got an M, so I could cancel all those M's out. 25 squared over 2. That's 12.5. So 124.26 minus 12.5 equals 9.8 times h. So let's do the math on that. And divided by 9.8. H equals 11.4 meters. That's how high that guy was on the bike, or the teacher. Okay, next question. Okay, we got Matt. Matt gets a job at a building after graduating at Loyola. He's in charge of lifting bricks to the 2nd floor. He gets a large mortar and uses it to lift the bricks. The mortar can lift 100 kilograms of bricks, 4.5 meters in the air every 6 seconds. So if you're lifting bricks, your work this time is going to, because they're asking for power, work over time. You're lifting bricks, so in this particular question, this is going to be mgh. So let's figure out the mgh. 100 kilograms of brick, 4.5 meters. So e.g. 100 kilograms times 9.8. Let's find how much work this motor's doing. 100 times 9.8 times 4.5 is 4,410 joules. And they want this one there. They want the power, so it's going to be 4410 over 6 seconds. That comes up to 735 watts. That would be the power. That's A. What's the power? And it's a 1 horsepower motor, which means that thing sucks back 746 watts of energy, or 746 joules every second. And they say, want to know what the efficiency is? Well, we're getting 735 units of work, but we paid for 746. So equals output. What's your result divided by your input? What did you pay for times 100? So I got out 735 watts of work lifting up bricks, but I paid for 746 in electricity. It's 98%. That's extremely good for a motor. So 2% of the energy is going to make the motor hot. Okay, most electric motors get a little warmer than that though. Okay, number 4. How much does it take? Minus 10 to 50 degrees. So draw myself a heating curve. I'm starting at minus 10. I'm ending at 50. Don't care about anything above or below that. Something special happens to water. At 0, it melts. So this question is going to have 3 parts. We're going to have heating up ice, melting water, and then heating up liquid water to 50, and then we shut it off. Okay, full heating curve, that's the heating curve. Even though it's all straight lines, but... So let's do step 1. Q equals mc delta T. Step 2, Q equals mLF for the freezing point of fusion. And 3 will be Q equals mc delta T. And this 2.6 kilograms of water. The C value for ice is not 4,200, it's 2,116. That's on the back of that one worksheet. And the ice went up 10 degrees. And this one, latent heat of fusion for ice is 330,000 joules for every kilogram of ice I'm melting, and I'm melting 2.6. This is regular water, it's going to be 4,200. And we went up from 0 to 50, so that's a gain of 50. Okay, let's see if we can write the answers over here. Slide another piece of paper under there. Okay, let's do the math then. 2.6, 2116, 10 times is 55,016 joules. Next one, 2.6 times 330,000 is 858,000 joules. And last one, to heat up the water is 546,000 joules. And then we just got to add up those three numbers. And we get 1,459,016 joules of energy to heat up the ice. From ice up to 50 degrees. Now we got one more question to do. Put that guy aside. Number 5. Even though the answer is right there. Well, we'll run through the process. So a person working in a mine discovers a 450 gram piece of iron. Okay. Let's draw a little picture here. 450 grams. The metal is heated to 460 degrees and placed in 1.2 kilograms of water at 12 degrees Celsius. So this guy plops into there, and they're both going to be together, so they're going to have some final temperature where they're together. Okay, this is 0.5 kilograms. The C for iron is 460 joules per kilogram degree Celsius. And delta T will be T final minus the initial temperature of 460. This guy, mass is 1.2. C, it's water, it's 4,200. And the delta T will be this T final, because they're both going to be the same, minus initial temperature of 12. And this guy's hot, he's cooler. This would be my loss. So Q loss equals, negative sign in front of that, equals Q gain. Okay, so let's fill in the formula. MC delta T equals MC delta T. You don't have to put all the subtitles. I'm going to have to say M of iron, C of iron, delta T of iron, because I've separated the page. This side is loss, that side's gain. All my givens are directly above it now, so I go times the C, T final minus 460 equals the mass of the water, heat capacity of water. Okay, the T final is going to have to be somewhere between 12 and 460. So this is going to give me a negative answer, which will cancel that negative sign, and this side will all be positive. So we can expand this through. If they were the same heat capacity, we could cancel. I guess you could cancel one of the zeros. Save yourself a little bit of work. Minus 460 equals 1.2. Again, now we just gotta go through this here. Expand through your brackets, expand through your brackets. So minus 207 T final plus 460 times 207 is 95,220 will equal 5,040 TF minus 5,040 times 12. 60,480. Let's collect our terms. I'm going to take all the TFs to the left, so it becomes positive and that becomes positive. So 60,480 plus 95,220 equals 5,040 TF plus 207 TF. Okay, now we can add them together. Final temperature of 29.7 degrees Celsius. Okay, That's the one for that guy.